Somewhere in a distant galaxy system nicknamed the Cosmic Owl, something massive is running. Not drifting, not orbiting peacefully at the center of its galaxy, the way supermassive black holes are supposed to behave, running at over 2 million miles per hour, tearing through space so violently that it's leaving a visible wound. Across the galaxy behind it, a trail of disturbed gas and newborn stars stretching for 200,000 light years. Scientists have now confirmed exactly what this object is, and the confirmation itself represents 50 years of theory finally catching up to direct, undeniable observation. This is the story of RBH1, the first confirmed runaway supermassive black hole ever detected, and why astronomers describe it as mind-boggling. If discoveries like this fascinate you, hit subscribe now, because we break down the most extreme, genuinely real phenomena in space every single week. Let's start with how this object was first noticed, because the discovery began almost by accident. Back in 2023, astronomer Peter Van Dokkum of Yale University and his research team were examining an archival image captured by the Hubble Space Telescope when they spotted something strange. A thin, razor-sharp streak of light extending for tens of thousands of light years away from a distant galaxy, with a bright, glowing knot of gas sitting at its far end. It looked almost like a contrail, the kind of streak a jet leaves behind in Earth's sky, except stretched across an unimaginable distance in deep space. Van Dokkum's team proposed a bold explanation. What if this streak was a wake, the visible trail left behind by something massive plowing through the thin gas surrounding its galaxy at tremendous speed, similar to the V-shaped ripple a speedboat carves across a lake? Specifically, they suspected this was the trail of a supermassive black hole that had somehow been ejected from its home galaxy entirely, now racing through intergalactic space and dragging a visible disturbance behind it. That was a genuinely dramatic claim, and not everyone in the scientific community was convinced. Like this video right now, if you want to understand exactly why scientists needed years of additional evidence before they were willing to confirm something this extreme. Skeptics offered alternative explanations. Some researchers suggested the streak might actually be a bulgeless galaxy, seen exactly edge-on from Earth's perspective, creating an illusion of a thin line rather than a genuine wake. Others proposed it could be the remnant of a galaxy that had been partially shredded by gravitational forces, with a black hole simply sitting at one end by coincidence, rather than actively causing the streak itself. Each of these competing explanations remained scientifically plausible using only the original Hubble imagery, since Hubble's instruments, while excellent at capturing detailed images, weren't capable of measuring something absolutely critical to settling the debate: motion. Don't forget to subscribe before we get into exactly how the James Webb Space Telescope finally resolved this 2-year scientific standoff, because the method involved is genuinely elegant. To prove this streak represented an actual runaway black hole rather than one of the alternative explanations, researchers needed direct evidence of movement, something demonstrating that whatever sat at the tip of this streak was genuinely speeding through space, actively displacing gas as it went, rather than simply being a static, misleading visual arrangement caught by chance. That's precisely the kind of measurement Webb's near-infrared spectrograph instrument, known as NIRSpec, was uniquely equipped to provide. Rather than simply capturing another image of the streak, Webb's team used NIRSpec to dissect the light coming from the object at the tip, breaking it down to measure exactly how fast the surrounding gas was moving, and in which direction. Using a well-established principle called blue shift, where light from an object moving toward the observer compresses toward shorter, bluer wavelengths, researchers were able to directly calculate the object's velocity for the first time. The results left no room for ambiguity. Webb confirmed the object, now officially designated RBH1, was moving at approximately 954 kilometers per second, roughly 2.2 million miles per hour, tilted at an angle of about 30 degrees toward Earth. Van Dokkum described the moment of confirmation in strikingly direct terms, explaining that with Webb's data, researchers had definitively confirmed a black hole existed at the tip of the streak, and that it was genuinely speeding away from its former host galaxy. Here's exactly why that specific speed matters so much. Make sure you're subscribed, because understanding the physics behind this number reveals just how extreme this object's situation genuinely is. A supermassive black hole remains gravitationally bound to its host galaxy under normal circumstances, anchored firmly at the galactic center by the combined gravitational pull of the billions of stars, gas clouds, and dark matter surrounding it. To actually break free of that gravitational grip entirely, an object needs to reach what astronomers call escape velocity, a specific speed threshold beyond which gravity simply can't pull it back. RBH1's confirmed speed of nearly 1,000 kilometers per second comfortably exceeds that threshold, meaning this black hole isn't just temporarily displaced from its galaxy's center, it's permanently, irreversibly escaping on a one-way trajectory into the emptiness of intergalactic space, never to return. Researchers estimate RBH1 carries a mass somewhere between 10 and 20 million times that of our own Sun, a genuinely massive object by any standard, yet one that Webb's data confirmed is now hurtling through space essentially unaccompanied by the galaxy that once anchored it. Van Dokkum captured the significance of this scale directly, stating plainly that the forces required to dislodge a black hole this massive from its home represent an almost incomprehensible amount of gravitational violence. So what actually kicked a black hole this massive out of its galaxy in the first place? Researchers believe the most likely explanation involves something called gravitational recoil, a phenomenon predicted by Einstein's general theory of relativity, occurring specifically when two supermassive black holes merge together. When two black holes spiral into each other and collide, the resulting merger releases an enormous burst of gravitational waves, ripples in space itself. Under certain specific conditions, particularly when the two merging black holes have misaligned spins, that burst of gravitational waves can be emitted asymmetrically, in significantly more energy in one particular direction than others. According to the fundamental physics of momentum conservation, that lopsided energy release then sends the newly merged black hole rocketing off in the opposite direction, similar to the recoil kick from firing a gun. Evidence suggests RBH1's ejection may have involved not just two, but potentially as many as three separate black holes interacting, each carrying a mass of at least 10 million suns, an interaction violent enough to generate the extraordinary kick needed to send the resulting merged object flying entirely free of its host galaxy's gravitational influence. What makes this discovery particularly significant extends well beyond confirming one single extreme object. Astronomers have theorized about the possibility of runaway supermassive black holes for roughly 5 decades, ever since the underlying physics of gravitational recoil was first worked out. But actually confirming a real-world example required exactly the kind of precise, direct velocity measurement that only became possible with an instrument as sensitive as Webb's NIRSpec. Van Dokkum described this milestone specifically, noting this represents the very first confirmation of a runaway supermassive black hole following 5 full decades of theoretical prediction. There's also visible physical evidence of the damage RBH1 continues causing as it plows through intergalactic gas. Webb's observations revealed a clear supersonic bow shock, a dramatic shock wave forming at the leading edge of the black hole's path, similar, in principle, to the sonic boom created by an aircraft breaking the sound barrier, except occurring on a scale spanning hundreds of thousands of light years. As RBH1 continues its journey, its powerful gravity compresses and disturbs the surrounding gas so intensely that it's actually triggering new star formation along its 200,000 light-year wake of freshly born stars as physical evidence of its passage. Researchers emphasize that RBH1 likely isn't a unique, one-of-a-kind anomaly. Rather, it may represent the first confirmed example of a population of similar runaway black holes scattered throughout the universe, objects that have simply proven extraordinarily difficult to detect until now, since a black hole traveling silently through empty intergalactic space without any surrounding gas to disturb and reveal its presence would remain essentially invisible using current observational techniques. Van Dokkum has specifically pointed to upcoming missions, including NASA's Nancy Grace Roman Space Telescope as promising future tools for hunting down additional examples, since Roman is specifically designed to survey enormous swaths of sky, unlike Webb's comparatively narrow, highly targeted field of view. Let's take a moment to understand exactly where RBH1 actually sits within the universe, because the scale involved adds important context to this entire story. The Cosmic Owl system, home to RBH1's former host galaxy, sits at a light travel distance of roughly 7.5 to 9 billion years from Earth. That means the light Webb and Hubble captured left this system billions of years ago, meaning astronomers are observing RBH1's dramatic escape not as it's happening today, but as it appeared in the extremely distant past, during an era when galaxy mergers and the resulting black hole collisions capable of producing objects like RBH1 occurred far more frequently throughout the universe than they do in the present day. The timing matters scientifically, because it connects RBH1 directly to one of the most active periods in the universe's entire history for galaxy growth and black hole formation. Understanding how frequently these violent black hole ejecting mergers occurred during this earlier cosmic era helps researchers build a more complete picture of how galaxies and their central black holes evolved together over billions of years, ultimately shaping the universe. Scientists observe today, including our own Milky Way galaxy, which itself harbors a supermassive black hole at its center. It's also worth understanding why confirming this discovery required such extensive, methodical scientific scrutiny before researchers were willing to publish their findings. Between the initial 2023 Hubble observation and Webb's confirming measurements, researchers conducted extensive follow-up work, including additional observations specifically designed to test and rule out the competing explanations skeptics had proposed. In one specific follow-up study, researchers used Hubble's ultraviolet imaging capabilities to check for a very particular predicted feature, a counterwake that should theoretically appear on the opposite side of the black hole if the runaway explanation was correct. When that specific search came back negative, it initially complicated the picture, requiring researchers to refine their understanding of exactly how this specific runaway black hole was interacting with its surrounding environment, before Webb's direct velocity measurements ultimately provided the conclusive evidence needed to settle the debate once and for all. That kind of rigorous, sometimes messy scientific process, complete with false leads, competing explanations, and years of careful, incremental verification, reflects exactly how genuinely extraordinary claims get properly established in astrophysics. Rather than accepting the most exciting, dramatic explanation immediately, researchers spent years systematically testing and ruling out more mundane alternatives, arriving at a runaway black hole explanation only after the evidence became genuinely undeniable. Looking ahead, researchers examining RBH1's data have submitted their formal findings to the Astrophysical journal letters, adding this discovery to the permanent peer-reviewed scientific record. Rather than treating this confirmation as a conclusion, astronomers view it as a genuine starting point, a template for identifying similar runaway black holes that may be hiding throughout the universe, waiting for future wider field survey telescopes to spot the same kind of distinctive stellar wake RBH1 left behind. For now, RBH1 continues its permanent, unstoppable journey away from the galaxy that once anchored it, carrying the confirmed physical evidence of one of the most violent events the universe can produce. A supermassive black hole merger powerful enough to eject the resulting object entirely free of its own galactic home, hurtling through the emptiness of intergalactic space at nearly 1,000 kilometers every single second, and likely destined to travel that way, essentially alone, for the rest of cosmic time. If this story left you as amazed as it left the researchers who confirmed it, make sure you're subscribed, because there are more genuinely extreme discoveries like this coming every week. Hit like, drop a comment letting me know what you think might be causing similar hidden runaways scattered throughout the universe. And I'll see you in the next video.